So we are going to begin by defining the lemniscate, and we are going to fix some positive real number a and consider the 2 points minus a0 and a0. Then the lemniscate is defined to be the locus of points xy such that the product of the distances of xy from minus a0 and a0 is fixed and is equal to a squared. Now, we can simplify this equation to obtain x squared plus y squared all squared equals 2a squared times x squared minus y squared. So we have been squaring both sides and doing some simplifications. So this is the Cartesian form of the equation of our lemniscate, and we can graph our lemniscate. And from the diagram or from the equation itself, we see that the lemniscate is symmetrical with respect to each axis, so that the perimeter of the lemniscate is 4 times the arc length in the first quadrant. So we are going to restrict ourselves to this first quadrant, and in the end we will multiply this length by 4 to obtain the perimeter. So to evaluate the perimeter of the lemniscate, we will make use of polar coordinates. So we define two new variables to transform our two variables xy into r and phi. And then our Cartesian equation takes this polar form, which is r to the power of 4 equals 2 times a squared times r squared times the cosine of 2 phi. And since we are restricting ourselves to the first quadrant, phi is restricted between 0 and pi over 4. And if we take the open interval, r is not 0, and we can divide both sides by r squared to find r squared equals 2 times a squared times the cosine of 2 phi. And as the cosine of 2 phi is positive when phi is in this domain, we can define a new variable psi and restrict it to be between 0 and pi over 2, such that cosine of 2 phi equals the square of the cosine of psi. And then we find that r squared equals 2 times a squared times the cosine squared of psi. So this is just this equation where we have replaced cosine of 2 phi by the square of the cosine of psi. And we remember that r squared equals x squared plus y squared. We can also consider x squared minus y squared and find that this is equal to r squared times the cosine squared of psi. And we can replace the value of r squared that we have just found to find that x squared minus y squared equals 2 times a squared times the cosine of psi raised to the power of 4. So we have two equations in x and y, which we can now solve simultaneously to obtain the following values for x squared and y squared in terms of a and psi. So as we need to evaluate the arc length, we are going to have to differentiate x and y, but before doing this, let us just note that we can rewrite these equations in a slightly different form. So to obtain this first equation here, we have made use of cosine squared of psi equals 1 minus sine squared of psi. And in the second equation, we have made use of the of this formula again, but then we have made use of the double angle formula to obtain this equation. And since psi is between 0 and pi over 2, we can just take square roots of both sides to arrive at these equations for x and y. So we take the positive square roots. And now we can differentiate these equations, and we start with the simpler one. So dy by d psi is equal to a times the cosine of 2 psi, and we can make use of the double angle formula to write cos of 2 psi as 1 minus 2 times sine squared of psi. Now we are going to differentiate x similarly, so it's slightly more complicated, but if we carry out the algebra to obtain as simple a form as we can, because we are subsequently going to square dx over d psi, we should be able to arrive at this quite nice expression for dx over d psi. So very well, as we are going to consider arc length, we need to consider this expression dx squared. So dx over d psi squared plus dy over d psi squared. And again, we need to carry out some tedious algebra. We need to square the expressions that we have arrived at, and then we need to add them. But we are rewarded in the end with a very simple expression. So we see that all along these terms in the curly brackets just evaluated to 1. So we find that this expression equals a squared over 1 minus a half times the sine squared of psi. So finally, we find that the arc length in the first quadrant is given by this integral. So we have just made use of this formula and integrated it. And theta here is restricted to be between 0 and pi over 2, but as we have mentioned at the beginning, by the symmetry of the Lemniscate with respect to the axes, we find that the perimeter is just 4 times this integral evaluated from psi equals 0 to psi equals pi over 2. So this is our expression for the perimeter of the Lemniscate, and this is an elliptic integral of the first kind. So complete elliptic integral of the first kind. And it has modulus 1 over the square root of 2. And what we are going to do now is to find other expressions for this integral. And to do this, we are going to first make the substitution z equals sine of psi. And this means that d psi will be equal to dz over the square root of 1 minus z squared. So we have taken the positive square root as psi is between 0 and pi over 2. So we are making a substitution in this integral, and this is what we get for our new integral. So the limit changed from 0 to pi over 2 to 0 to 1. And in this integral now, we are going to make yet another substitution. So we make the substitution y equals the square root of 1 minus z squared. And then z is equal to the positive square root of 1 minus y squared, since z is between 0 and 1. And dz equals minus y times dy over the square root of 1 minus y squared. And this means that this expression here in the denominator equals 1 over the square root of 2 times the square root of 1 plus y squared. And this is very nice because when we replace all these substitution in this integral, we will end up with this very nice integral, which is the integral from 0 to 1 of 1 over the square root of 1 minus y to the power of 4. So if it was a power of 2, we would know how to use the arc sign to evaluate the indefinite integral. But when the power is 4, we don't really know So we can't use our circular functions in the usual way to find an indefinite integral. So this is one reason why this integral is very interesting. But so far, this is what we have found for the perimeter of our lemniscate. So we have obtained these two integrals to express the perimeter of the lemniscate. And if we want to actually calculate the perimeter, one thing which we could do is use the binomial theorem in this integrand and then integrate term-wise. And we find this very nice infinite series for the perimeter. So we know that the coefficients 1, 5, 9, 13, and so on are an arithmetic progression with difference 4. Now we are going to note one more thing about the Lemniscate perimeter. So that's if we recall the definition of the beta function, which is really this quotient of gamma functions. And this is equal to this integral here. And in this integral, we are going to make this substitution. So we are going to change t into t to the power of 4 to rewrite this integral as this integral. And we are going to put x equals 1 over 4 to eliminate this term. And we are going to put y equals a half to make this, to obtain this integral. So we have been dealing with this integral previously. And we see that we can express this as explicitly in terms of gamma functions as follows. And now we recall that the value of gamma of a half is equal to the square root of pi. So that's like the factorial of minus a half. And then we can also make use of Euler's reflection formula, which is the following. And we can replace P equals a quarter to find that the product of gamma of 1 over 4 times gamma of 3 over 4 equals pi times the square root of 2. Which means that the expression that we have found can be written as gamma squared of 1 over 4 times the square root of 2 pi. And overall, this means that the perimeter of our lemniscate is equal to each of these three expressions. So we found this initially, we made substitutions to find this integral, and finally we used the gamma function to express the perimeter in terms of the gamma function as follows.